q dot gives you the linear and angular velocities. And we will see that essentially this Jacobian is really related to the way the axes of this robot are designed. And once you understood this model, you are going to be able to look at a robot and see the Jacobian automatically. You look at the machine and you see the model automatically through this explicit form that we will develop to compute those linear velocities and angular velocities through the analysis of the contribution of each axis to the final resulting velocities. So we will also discuss inverse kinematics, although we are not going to use it extensively as it has been done in industrial robotics. We will examine inverse kinematics and look at the difficulties in terms of the multiplicity of solutions and the existence and of those solutions, and examine different techniques for finding those solutions. So again, the inverse kinematics is how I can find this configuration that correspond to the desired end effector position and orientation. And then using those solutions, we can then do this interpolation between where the robot is at a given point and then how to move the robot to the final configuration through trajectory that are smooth both in velocity and acceleration and other constraints that we might impose through the generation of trajectories both in joint space and in Cartesian space. So these, I'm going backward now. So these will result in those smooth trajectories that could have via points that could impose upper bound on the velocities or the accelerations, and resolving all of these by finding this interpolation between the different points. And that will bring us to the midterm, which will be on Wednesday, February the 13th. It's not a Friday 13th, it's Wednesday, so no worries. And it will be in class, and it will be during the same schedule. Now, for the midterm, the time of the class is short, and you have really to be ready, not really like to discover how to solve the problem, but really immediately to work on the problem. So that's why the review sessions are very important to prepare you for the midterm, to make sure that you will be able to solve all the problems. Also, we make sure that the size of the problem fits with the time constraints that we have in the midterm. After the midterm, we will start looking at dynamics, control, and the other topics. And first, what we need to do is I'm not sure how many of you are mechanical engineers. Let's see, how many are mechanical engineers in the class? Good. And how many are CS? Wow. That is about right. We have half of the class who's familiar with some of the physical models that we are going to develop, and some others who are not. But I'm going to assume that really everyone has no knowledge of dynamics or control or kinematics, and I will start with really the basic foundation. So you shouldn't worry about the fact that you don't have strong background in those areas. We will cover them from the start. We will go to what is the inertia, what is how do we describe accelerations, and then we will establish the dynamics, which is quite simple. Anyone recalls a Newton equation? So let's see, what is the relationship between forces and accelerations? You need to know that, otherwise. Okay, I need to hear it. Someone tell me. Okay, good. Mass acceleration equal force. Well, this is all what you need to know. If you know how one particle can move under the application of a force, then we will be able to generalize to many particles attached in a rigid body, and then we will put them into a structure that will take us to multi-body system, articulated multi-body system. So we will cover these without difficulty, hopefully. The result is quite interesting. So this is a robot. This is a robot that is controlled not by motors on the joints, but by cables. So really the active part of the robot is from here to there, and here you see all the motors and cables driven system that is on the right. Now, if you think about the dynamics of this robot, it gets to be really complicated. So you see on the right here, so this is the robot, and here you have some of the descriptions of, well, you cannot see anything probably, but you have all the descriptions of, for instance, what is the inertia view from the first joint when you move. So this inertia is changing as you move. So imagine if I'm considering the inertia about this axis, right? If I'm deploying the whole arm, the inertia will increase. If I'm putting the arm like this, I will have smaller inertia about this axis. Bigger inertia, smaller inertia. So the inertia view from a joint is going to depend on the structure following that joint. And we will see that essentially all of this will come very naturally from the equations that will be generated from the multi-body system. But all what we are going to use for this is a very simple description that, again, will allow you to take a look at this robot and say, oh, this is the characteristics, the dynamic characteristics of this joint, and you can almost see the coupling forces between the different joints in a visual form that all depend on those axes of rotation and or translation of the robot. And this comes through the explicit form of dynamics that we will develop. This representation is an abstraction of the description that we will do with the Jacobian. So I said in the Jacobian case, we will take a description that is based on the contribution of each joint to the total velocity, and we will do the same thing. What is the contribution of each link to the resulting inertial forces? So when we do this, we will look at what is the contribution of this joint and the attached link and the contribution of the others, and we just add them all, and you will see the structure coming all together. So that is a very different way than the way Newton and Euler formalize the dynamics, which relies on the fact that we take each of these rigid bodies and connect them through reaction forces. So if you take all the links and if you remove the joints, you get one link, but when you remove the joint, you substitute the removal of the joint with reaction forces, and then you can study all these reaction forces and try to find the relationship between forces and acceleration. Well, this way of, which is called the recursive Newton-Euler formulation, is going to require elimination of these internal forces and elimination of the forces of contact between the different rigid bodies. And what we will do instead, we will go to the velocities and we will consider the energy associated with the motion of these rigid bodies. So if you have a velocity v and omega at the center of mass, and you can write the energy, the kinetic energy associated with this moving mass and inertia associated with the rigid body. And simply by adding the kinetic energy of these different links, you have the total kinetic energy of the system. And by then taking these velocities and taking the Jacobian relationship between velocities to connect them to joint velocities, you will be able to extract the the mass properties of the robot. So the mass matrix will become a very simple form of the Jacobian. So that's why I'm going to insist on your understanding of the Jacobian. Once you understand the Jacobian, you can scale the Jacobian with the masses and the inertias and get your dynamics. So going to dynamics is going to be very simple if after the midterm you really understood what is the Jacobian. The dynamics, this mass matrix associated with the dynamics of the system comes simply by looking at the sum of the contributions of the center of mass velocities and the Jacobian associated with those center of masses. In control, we will examine, well, I'm going to assume also that little background in control, so we will go over just a single mass spring system and analyze it, and then we will examine controllers such as PD controllers or PID controllers, proportional derivative or proportional integral derivative, and then we apply these in joint space and in task space by augmenting the controllers with the dynamic structure so that we account for the dynamics when we are controlling the robot. And that is going to lead to a very interesting analysis of the dynamics and how dynamics affect the behavior of the robot. You can see that the equation of motion for 2 degrees of freedom comes to be sort of 2 equations involving not only the acceleration of the joint, but the acceleration of the second joint, the velocities, centrifugal Coriolis forces, and gravity forces. And through this, all of these will have effect, dynamic effect and disturbances on the behavior, but we will analyze a structure that would allow us to design torque 1 and torque 2, the torques applied to the motor, to create the behavior that is going to allow us to compensate for those effects. So all of this are descriptions in joint space. That is descriptions of what torque and what motion at the joint. And what we will see is that in controlling robots, we can really simplify much further the problem by considering the behavior of the robot in terms of its motion when it's performing a task. That is, we can go to the task itself. The task in the case of the example I described is how to move the hand to this location without really focusing on how each of the joint is going to move. And this concept can be captured by simply thinking about this robot, this total robot, as if the robot was attracted to move to the goal position. This is similar to the way humans operate. When you are controlling your hand to move to a goal position, essentially you are visually servoing your hand to the goal. You are not thinking about how the joints are moving. You are just moving the hand by applying these forces to move the hand to the goal position. So it's like holding the hand and pulling it down to the goal. And at the initial configuration, you have no commitment about the final configuration of the arm. You are just applying the force towards the goal, and you are moving towards the goal. So simply by creating a gradient of a potential energy, you will be able to move to that configuration. And this is precisely what we saw in this example, in the example of this robot here. So this motion that we are creating, so if we are going to move the hand to this location, we are going to generate a force that it's like a magnet. It will pull the hand to this configuration. But at the same time, you have, in this complex case, you have a robot that is standing and it has to balance. So there are other things that needs to be taken into account. And what we are doing is we are also applying other potential energies to the rest of the body to balance. So when we apply this force, you see it's just following, it's like a magnet. It's following this configuration. there is no computation of the joint positions. Simply we are applying these attractive forces to the goal. You can apply it here, apply it there, or apply it to both. Now, obviously, if you cut the motors, it's going to fall, and it behaves a little bit like a human, actually. So when you cut the muscle, it starts. In fact, this environment we developed is quite interesting. You can not only interact with it by moving the goal, but you can go and pull the hair. Ouch! You can pull anywhere. When I click here, I'm computing the forward kinematics and the Jacobian, and I'm applying a force that is immediately going to produce that force computed by the Jacobian on the motors, and everything will react in that way. So we are able to create those interaction between the graphics, the kinematics, and apply it to the dynamic system, and everything actually is simulated on the laptop here. So this is an environment that allows us to do a lot of interesting simulations of human-like structures. And so you apply the force and you transform it. As I said, the relationship between forces and torques is also the Jacobian. So the Jacobian plays a very important role. And then to compute the dynamics, all what we need to do is to understand the relationship between forces applied at the end effector and the resulting acceleration. Now, when we talked earlier about Newton's law, we said force, mass, acceleration equal force. And the mass was scalar. But this is a multi-body system. And the mass is going to be a big M mass matrix. So the relationship between forces and acceleration is not linear. That is, forces and acceleration are not aligned because of the fact that you have a matrix. And because of that, you need to establish the relationship between the two. And once you have this model, you can account for the dynamics in your forces, and then you can align the forces to move, to be in the direction that produces the right acceleration. Finally, we need to deal with the problem of controlling contact. So when you are moving in space is one thing, but when we are going to move in contact space, it's a different thing. Applying this force put the whole structure under a constraint, and you have to account for these constraints and compute the normals, so to find the reaction forces in order to control the forces being applied to the environment. So we need to deal with force control, and we need to stabilize the transition from free space to contact space. So that is, we need to be able to control these contact forces while moving. And what is nice, if you do this in the Cartesian space or in the task space, you will be able to just merge the two forces together to control the robot directly to produce motion and contact. I mentioned that we will discuss some other topics. There will be a guest lecturer that will talk about vision in robotics, and we will also discuss issues about design. I would like to discuss a little bit some issues related to safety and the issues related to making robots lighter with structures that become safer and flexible to work in a human environment. Also, we need to discuss a little bit about motion planning, and especially if we are going to insert those robots in the human environment, we need reactive planning. And there is, in this video, you can see how a complex robotic system is reacting here to obstacles that are coming at it. It's moving away from those obstacles. And this is simply done by using the same type of concept that I described for moving to a goal position. I said we can create an attractive potential energy. In here, to create this motion, we are creating a repulsive potential energy. So if you put two magnets north-north, they will repel. And this is exactly what is happening. We are creating artificially those forces and making the robot moves away. But if you have a global plan, you need to deal with the full plan so that you will not reach a local minima. And we then apply this technique to modify all the intermediate configurations so that a robot like this would be moving to a goal position through this plan. And when an obstacle or when the world is changed, the trajectory is moving, the hand is moving, and all of this is happening in real time, which is amazing for a robot with those number of degrees of freedom. The reason is, I'm not sure if you're familiar with the problem. Oh, sorry, let me just stop it here. The problem of motion planning in robotics is exponential in the number of degrees of freedom. So usually if you want to replan a motion when one obstacle has moved, it would take hours to do, and for a large number of degrees of freedom. And here we are able to do this quite quickly because we are using the structure and we are using this concept of repulsive forces that modifies future configurations and integrate. So this is an example showing Indiana Jones going through the obstacles modified by, in real time actually, modified all these configurations. And all these computations are taking place because in real time, because we are using this initial structure and incrementally modifying all the configurations. Another topic that I mentioned slightly earlier is the implication on digital modeling of human. And learning from the human is very interesting and very attractive to create good controllers for robots, and also understanding a human motion. In fact, currently we are modeling Tai Chi motion and trying to analyze and learn from those motions. So you can go from motion capture to copying that motion to the robot, but in fact you will end up with just one example of motion. But the question really is how you can generalize, not just have one specific motion. And to do that, if you want to generalize, you need to take the motion of the human from motion capture and map it not to the robot, but to a model of the human. So you need to model the human, and modeling the human involves modeling the skeletal system. So we worked on this problem. So now you have, this is a new kind of robot system with many degrees of freedom, about 79 degrees of freedom. And all of this is modeled through the same model of kinematics, dynamics, and then you can model the actuation, which is muscles now. And from this you can learn a lot of things about the model, and then now you can control it. You can control, this is synthesized motion, and you understand how this is working. You just guide the task, and then you have the balance taking place through other minimization of the remainder of degrees of freedom. And then you can take those characteristics and map them to the robot, scale them to the robot, not copying trajectories, but copying the characteristics of the motion. It's quite interesting. We'll discuss also a little bit about haptics. This will be more developed in advanced robotics later in the spring, but haptics is very important, especially in the interaction with the environment, the real physical environment. So you go and touch, and now you have information that allows you to reconstruct the surface and move over now more the descriptions of what you are touching and what normals you have. Oh, well, contact. Quite amazing. What is amazing about this is done in real time. So someone from the automobile industry was visiting us and said, why now you have model of skeletal systems and good models for resolving contact, why don't you use them for crashes instead of using dummies, right? So, ouch. But it's only in the model. So, well, there is a lot that will come later, but I will mention a few things about the interactivity also with obstacles and how we can deal with those issues, and then combining locomotion, walking with manipulation, and dynamic skills like jumping, landing, and all these different things. Okay, so what is happening here? Okay, this is a different planet. I'm going to just, okay. And that will take us to the final, which will be on Friday, the 21st of March. And the time is different. It will be at 12:15. We will announce it. And hopefully we will have, again, a review session before that. It is on the schedule. And that review session will review previous finals. And here you will have enough time, enough time to solve some good problems. So, by the way, not everything that you see in simulation is valid for the real world. And let's see, how many skiers we have here? Skiers. That's all? I would have thought it. Oh, okay. Okay. Does it ski? Let's see the ski. Don't do that. All right. I will see some of you on Monday. Okay.